All right. Hello, everybody. Welcome to the Penn State CTSI BERD seminar series for this fall semester. This seminar series is organized by Dr. Lan Kong and me, and my name is Jay Zhu. Both of us are faculty members at the Department of Public Health Sciences at Penn State. Let me just go through some basic logics. Because of the COVID, this seminar is actually held as a webinar. So through the Zoom webinar, it is being recorded automatically, and all the attendees are muted except for the panelists. But if you have any question, please feel free to submit your questions anytime using the Q&A, the Q&A box. The speaker will actually check the Q&A box sometimes during his talk. You can register for future seminars at ctsi.psu.edu and then go to the research support and go to seminars, and you can find the topics of future seminars. And you actually receive the slides and similar feedback after the seminar. All right. Today, we are very happy to have my colleague, Mr. Alan Kunselman here. Mr. Kunselman is the Director of Biostatistical Consulting Service in the Department of Public Health Sciences at Penn State, a position he has served since 2005. He's a highly experienced applied biostatistician and has worked on many different research areas, including cardiovascular disease, obesity, and pediatric research. He has more than 270 peer-reviewed publications over the years. The title of Mr. Kunselman's lecture today is the basics of randomization and sample size estimation. For many researchers, those two topics are very important in the designing stage of their research projects. Mr. Kunselman will share his expertise with us regarding how to handle those two problems in a statistician's point of view. So without further ado, let's welcome Mr. Kunselman. Here, I'm going to stop sharing my screen, and then Mr. Kunselman can start sharing his. Go ahead, Alan.
Great. Just 1 second.
All right. You want to share the other? Oh, yeah. There we go.
You see the slides okay?
Yeah, I can see it. Go ahead.
Oops. So thank you for the introduction, Jay. I appreciate it. And I just want to let everybody know that, as the topic says, this is the basics of randomization and sample size estimation. So it's not going to be in-depth formulas and details statistically, but just like an overview to give you an idea of things you might want to talk about a statistician on your project and help you understand the basics of these concepts. So the first topic I want to talk about is simply just randomization. And a randomized controlled trial is considered the strongest design for evaluating the effects of an intervention. And advantages of randomization are they avoid selection bias, where selection bias occurs if the allocation process is predictable. So for example, if you thought you were doing a randomized study and you're going to assign everybody treatment A on odd days of the month and everybody else treatment B on even days of the month, That's predictable because as a physician or a researcher, you would know that, oh, those on the odd days of the month get treatment A and even days get treatment B. So that would be a selection bias. So good randomization will avoid that. It also allows you to produce comparable groups in terms of both known and unknown prognostic factors. So what that means is basically you'll minimize accidental bias or confounding. And we'll talk more about that as we go on. And a third point, an advantage of randomization is it adds validity to the statistical tests you'll be performing on your research data. And there are two main branches of randomization procedures. One's called fixed allocation and the other's adaptive. So fixed allocation is probably the most common, and it's probably one you've heard about the most. And what it does, it assigns the interventions to subjects with a pre-specified probability, and it's typically equal. So for example, if you're trying to design a trial with two independent groups, you probably have it for where 50% of the people get assigned treatment A, 50% would be treatment B. And the reason it's fixed is because the allocation process is not altered during the trial. That means if with two treatments, that 50-50 choice is maintained throughout the entire trial. And there are many methods of fixed allocation, and I'm going to talk about 4 of them very briefly. So there's simple or complete randomization, blocked or permuted block randomization, stratified randomization, and stratified permuted block randomization. So in the first case, the simple or complete randomization, what you do is you make a new treatment assignment without regard to those already made. So what does that mean? So let's, for example, say we have 2 treatments, A and B. And for each new subject randomized, the probability that the subject's assigned to either treatment could be 50-50. So like a coin flip. So the first person comes in, heads they get treatment A, tails they get treatment B. Flip the coin, it's an A, so the first person gets heads. Second person comes in, flip the coin, it may come up tails, so the second person gets treatment B. So then you end up with this sequence of the randomization list. So if we had 10 subjects, if you flip the coin 10 times, the pattern might be the first person would get A, the second person would get B, A, B, A, etc. So an advantage of this, it's very easy to implement randomization scheme. The disadvantage is you have the potential for substantial imbalance in the number of subjects, or we'll talk about it a little bit, distribution of prognostic factors between the groups, especially for small studies. And these imbalances do not mean a statistical test will be invalid. So for example, if you plan to do a 2-sample t-test to test the difference in means between your 2 groups, that's still a valid statistical test. However, the imbalances do reduce the ability to detect a true difference. Basically, you're reducing the power of your study, which we'll get into the second topic, which is sample size estimation. But as you can see from this example I have here with these 10 subjects, it turned out there were 4 A's and 6 B's. So it didn't turn out to be 5 A's and 5 B's. And you can just think about it simple. If I need to randomize 10 subjects and I flip the coin 10 times, you could easily get 2 heads and 8 tails, or translating it to the letters, 2 A's and 8 B's, which wouldn't be a balanced randomization, and you get less power. So what can we do to help fix this? We can do blocked or permuted block randomization. And what this does is it adds a simple constraint that improves. So a block contains a pre-specified number and proportion of treatment assignments. The size of each block must be an exact integer multiple of the number of treatments. So for example, if you have 2 treatments, your block size, if you have 3 treatments, the block sizes would need to be 3, 6, 9, 12, and so on. So you can use fixed block or variable block sizes. And I'll give you an example of this in the next slide, but a variable block size means the allocation is even harder to predict than a fixed blocks design. And these sequences of blocks make up your final randomization list for your subjects. After all assignments have been made in each block, the treatment groups will be balanced. So the easiest way to think about this is an example again. And we want to randomize a total of 20 subjects, 10 in each group. And we want to use a fixed block size of 4. So with a fixed block size of 4, there are 6 possible permutations for 2 treatments. You could have AABB, ABAB, ABBA, etc. And you can label these with the numbers 1 to 6. So AABEB would be 1, ABAB would be 2. And what the randomization does, using a pseudo random number generator, you would select 5 of these numbers with replacement. And why 5? Because if our block size is 4, 5 blocks times 4 in each block is 20, which gives us our total number of 20 subjects. So let's assume this random number generator, with replacement, pick the numbers 2, 1, 4, 2, 5. Then our final randomization list will look like this. The first block would be 2, so it's 8, and then it picked 4, which is BBAA. So at the end of the study, your list will be the very first person will get an A, the second person will get a B, up to the 20th person will get assigned treatment A. And what you can see in each of these blocks, it's balanced. There's 2 A's and 2 B's in each of these blocks of size 4. So at the end of the study, we have a balanced design of 10 A's and 10 B's. So we avoid that possible mismatch with simple randomization. I'm trying to check questions. Is there an easy way? Okay, sorry, no questions so far. So moving on, the next step we could do stratification. And what stratification does is it balances several clinically important prognostic factors across the treatment groups. So what are prognostic factors? Well, these are factors that are known to be strongly associated with the outcome of interest. So for example, say we had 2 treatments, A and B, and our primary outcome was forced expiratory volume, FEV. Well, prognostic or possible confounding factor would be the patient's smoking status, because smoking status is highly associated with the outcome of FEV. And at the end of the study, we want to know if treatment A or treatment B works regardless of their smoking status. So one way to address this is through a stratified randomization. So for every relevant prognostic factor combination, we can find an individual stratum with blocking in each stratum. Treatment assignments will be balanced with each stratum, yielding balanced prognostic factors in each group as well. So we have the possibility of treatment imbalances. So what this next bullet point means is the more stratification factors you have, the higher probability we'll see big imbalances in a number of people in group treatment A and treatment B. So stratified randomization is really only good if you have a limited number of stratification factors. There are better methods, which we'll get into, which is the adaptive randomization for handling multiple stratification factors. But for typical studies, I recommend having only 2 to 4 stratification factors at most. And I like to stick with, 1 stratification factor with 2 levels, or 2 stratification factors with 2 levels each, so a total of 4 strata. So to understand this a bit better, let's look at our example. So if we're back to we want to randomize 20 subjects to treatments A and B, but now we have this stratification factor of smoking status. We have smokers and non-smokers. And let's just assume at the end of this study, we ended up with 4 smokers and 16 non-smokers. Our stratification list could show up to be, the 4 smokers may have gotten this pattern, ABBA, and the non-smokers 16 have this randomization list. But you'll see within each strata, within the smokers, we have 2 A's and 2 B's. And within non-smokers, we have 8 A's and 8 B's. So at the end of the study, we still have our 10 A's and 10 B's, but it's also balanced within each of these stratification factors. And I don't have a slide for this, just to extend this. The more stratification factors you have, like I mentioned before, you have chance for imbalance. So let's assume we had smoking as stratification factor, a smoker, non-smoker. We have age greater than 50 or age less than 50 as a stratification factor. We have gender, male, female as a stratification factor. And we have diabetic status, or you have diabetic, yes or no as stratification factor. The more you get, the chances are some of these strata will have very few patients. So for example, at the end of our study, we may only have one person who is a smoker, who is non-diabetic, who's a female, who's greater than 50. And that one person, that one strata may got an assigned treatment A. And we have one other person who's a male smoker, who is diabetic, and who's less than 50. And by chance, they may have also gotten assigned A. So a lot of these like really small levels might only have one assignment, and it could be the same treatment, and just yet more imbalance with the more factors you have. So what's a different method to maybe solve some of these problems? Well, it is adaptive randomization. And I wanted to point out before I get into adaptive randomization, some of you may be familiar with the REDCap database, and it's recommended it for Penn State Hershey Medical Center research studies to use REDCap because it's a very good database to use. And REDCap has a randomization module built into it, but it can only do fixed randomization, fixed allocation randomization. So it can do the simple randomization, stratified randomization, permuted block stratified randomization. So things we just talked about, REDCap can handle and do well. What REDCap cannot do is what we're going to talk about next, which is adaptive randomization. And some of the reasons are not just REDCap, but what is adaptive randomization? It changes the allocation probabilities as the study progresses. And I'll explain that more in a second. So advantages, it's very flexible. It's better balance for especially a large number of covariates. So my example of having those 4 stratification factors of gender, diabetic status, smoking status, and age. If you had even more factors, adaptive randomization handles multiple covariates much better than fixed allocation. Disadvantages, it's much more complex to do. It's much more difficult to implement than fixed allocation methods. And by difficult, it's costly. Like I said, REDCap can't do it. So you probably need to have somebody program a customized randomization module to do it for you, so it could get expensive doing adaptive randomization. So there are 4 major types of adaptive randomization. Oh, I'm sorry, hold up a second. I see we have a question. So the question is, comparing with block randomization, why not just sample 10 from 20 without replacement to treatment A? You could do that, but the big thing behind randomization is you do want replacement. You want to pick out the same idea. I think you could get around it with what you're saying. Why not just sample 10 to 20 without replacement? But it's not the ideal method, when especially when you get into larger studies. So I'll come back and answer your question more a little bit after I talk about this slide. So as I mentioned, there's 4 major types of adaptive randomization. Restricted randomization, which uses past treatment assignments to select the probability for a future treatment assignment with the goal to balance the number of subjects across the treatment. And an example of this is a biased coin design. So what does that mean? So this means that, let's assume we have 2 treatments again, A and B, and we want to randomly assign those people treatment A and B. Well, the very first person, it's truly a 50-50 coin flip. So let's assume we flip a coin and heads is treatment A, tails is treatment B. The first person gets assigned to treatment A. What restricted randomization does is it looks at then a second person comes in. What restricted randomization does, it looks at the prior treatments and figures out how to do the next person. So because the first person was assigned to treatment A, the second person, the probability isn't 50-50 anymore. It may be, well, we already have 1A in the study. So now the second person, it's going to be a 51% chance to get treatment B and a 49% chance to get treatment A. That's the biased coin. So we flip this biased coin, and let's say it comes up A again. So now the first two people are A, and the third person's ready to be randomized. Now the program's thinking, or the randomization process is, well, we have two A's, we don't have a B yet, we really should get a B, so let's increase that probability. So now it might be 55% chance to get an A and 45% chance to get a B. You flip the coin and it comes up B this time. So our first three people were A, B. And now the fourth person comes in. We still have more A's and B's, but it's not as bad as before. So it might drop back down to the 51% chance to get a B, 49% chance to get an A. So that's what it's doing. It's adapting. As each person comes in, it looks at the previous treatment assignments and figures out new probabilities to assign the next person. So at the end of the study, you do have balance of half your people on treatment A and half the people on treatment B. The next extension of this is covariate adaptive randomization. So what this is, it says, is it uses the past treatment assignments and the patient covariate values, or our prognostic factors, to select the probability of a future treatment assignment with the goal to balance treatment assignments within covariate profiles. A term you may have heard for this is called minimization. I really don't do cancer research anymore, and I'm not sure they still do this, but I guess a decade or so ago, multi-center cancer trials, minimization, this method was the de facto form of randomization for multi-center cancer trials. I can't say if they still use that or not because I don't do really research in that area. But what it does, again, is it takes, the first person gets assigned a treatment, say A, and they're a smoker. So then the second person comes in and says, okay, we need to assign a treatment. The first person was A and a smoker. This next person we know is not a smoker. And it readjusts the probability. So it's balancing on both the treatment assignment and the prognostic factors. And that's why this is the method to use when you have a lot of prognostic factors. It handles that much better than the fixed allocation stratification method. The next adaptive randomization process is called response adaptive randomization. So what it does is it uses past treatment assignments and patient responses to select the probability of the future treatment assignment with the goal to maximize the power and minimize expected treatment failures. So what this does, again, it takes the previous assignment. So let's assume the first person comes in, they got randomized to treatment A. But then it looks at when this patient finishes the trial, did they have a successful response, yes or no? So that's the response. And what it's trying to do is say, you may have heard the term play the winner. So let's assume that we have a trial, we have 5 different treatment groups, A, B, C, D, E, and A, B, C, D, and E. And what it's trying to do is assign more patients to the arms of the trial that seem like they're being successful, where the patients are responding, and less weight is given to the treatment groups that aren't succeeding. So as you go along in time, treatment E at all, as the study progresses, you might not be assigning anybody to treatment E any longer. And you're like playing the winners, like treatments A, B, and C might be performing well. So you want to keep feeding patients into those arms. And D and E might not be performing well. So it's going to downweight, and you might very rarely assign somebody to those treatments. So if you want to know more about that, you can do a Google search on play the winner randomization methods. It's not done very often. I think I've only really seen it in cancer studies, but it's another method. And then the last one is covariate adjusted response adaptive randomization. And all that is, it's basically a combination of the covariate adaptive randomization and the response adaptive. So it's taking previous treatment assignments, your patient's prognostic factors, and then how the patients actually responded to the therapy to assign them. And as I mentioned briefly, if you plan to use REDCap cannot do any of these adaptive randomization methods, but they can do the fixed allocation methods. So I'm going to pause here right now and see if anybody has any questions, because this is the end of my brief basic overview of randomization and how it actually works and how it makes your study a little stronger. Does anybody have any questions at this point before we move into the next topic?
Helen.
Yes.
Yeah, just a quick comment. I think the minimization, because I do the cancer-related research, the minimization is still used. It actually occurred to me that one of my research projects, we actually have lots of the covariates can be served as the confounders, and we do want to adjust for those covariates. And we initially thought about the stratified randomization, but then in a research meeting with the FDA experts, they actually point out that we can consider the minimization method. So it is still being used.
Right, and I think when you met with those people, it's probably because you have so many covariates, and stratification is not a good process if you have a lot.
Yeah, especially consider the sample size. So
I'm curious, did you write the program to do this, or are you using?
No, they actually need a separate team to handle this randomization. So it's beyond one man's job. So they are going to hire like an entire team to handle this.
Right. As I said, I think this minimization is a very good method to use. It's probably one of the strongest, but the downside is it's much more complicated.
Yeah, it's more complicated, and
it's not simple to implement.
Yeah, exactly. All right. Thank you.
But like I said, cancer trials usually have a lot of covariates they're trying to adjust for, and that's why they. Good. Any other questions? So if not, I'm going to move into the next basic topic, which was sample size estimation. And like I said, there aren't any formulas in here. This is more of an overview of things to think about and talk with your statistician about when you start doing your own research study. So why do we need to worry about sample size and power when we do our studies? Well, there are scientific reasons. So the study has to be big enough to statistically detect a scientifically or clinically meaningful effect. But the study should not be too large where the effect of a little scientific importance is nevertheless statistically detectable. So what does that mean? So I like to use the example of systolic blood pressure. Let's assume we have a study where we want to look at severely hypertensive subjects, and we want to compare a new drug to a placebo to lower your systolic blood pressure. Let's assume that the placebo at the end of the study lowered the average systolic blood pressure of the patients on placebo dropped by 1 millimeter of mercury. And the new drug, it dropped by 21 millimeters of mercury. So the difference, 21 minus 1, is 20 millimeters of mercury. Most people would probably think, well, that's an important difference. 20 millimeter of mercury difference between the new drug and placebo. It looks like the drug is working. But if you didn't have enough subjects and your p-value was 0.65, you didn't really prove anything. So you found a big effect size, but you didn't have enough subjects to find a significant effect statistically. You didn't find a small enough p-value. So how's it too big? Same example. If I have 5,000 people on treatment A and 5,000 people on if I have 5,000 people on a placebo and 5,000 people on a new drug, I could probably find a p-value of less than 0.01, but the difference between the placebo and a treatment group might be 1 millimeter of mercury, which nobody cares about. So if you have a very large study, you can find very small differences between the groups, which are statistically significant, but clinically irrelevant. So there's a balancing act. You need a study to be big enough to find a significant p-value, for example. You don't want it so large that you're finding trivial effects. And then likewise, there are economic reasons. An undersized study will waste resources and money by not having the capacity to produce a definitive result, or an oversized study is going to use more resources and money than necessary. And then you have ethical reasons. The undersized study exposes subjects to potentially harmful treatments without advancing knowledge, meaning it's like, you didn't find a definitive result, why did we expose these people to maybe a harmful treatment? Whereas the oversized study exposes more people than necessary to potential harmful treatment, or it could possibly deny a potentially beneficial treatment. So this last phrase about potentially beneficial, let's assume we're a big pharmaceutical company. We have lots of money. And I have this big, huge study, and it's going to take 15 years for everybody to finish through the treatment, because I have to get a sample size of 10,000 people. Well, if we could have did a sample size of 5,000 people and showed the same result and finished the trial in half the time, then you could have gotten that product to market and helped actual patients maybe 5-10 years faster than you could if you did this overblown, too large of a study. So that's what I mean by holding back a potentially beneficial treatment, that you could have shown your result much earlier than extending the study, going on and on to find the same effect. I hope that made sense. So in short, sample size estimation is important for your study design to ensure validity, accuracy, reliability, scientific and ethical integrity. And grant reviewers and IRBs are looking for sample size and power calculations, especially for any prospective study. So how do we do sample size estimation? There are many approaches. I'm just going to list 3 of them here, but we'll only focus on one. One type to do sample size estimation is precision of the estimate. So you specify a desired width of a constant confidence interval. So an example of this would be, say you think the percentage of diabetics that come to your clinic is 40%, but you want the margin of error to be plus or minus 1%. So you want to be really 95% confident that the percentage of diabetics that you'll see in your clinical practice is between 39 and 41%. That's a confidence interval, and you can do a sample size calculation looking at that. Another approach is to use a Bayesian approach to optimize a utility function, for example, a cost function. And a third approach, and this is by far the most common approach and the one we're going to talk about today, is the power of the test of a hypothesis. So what are some elements for the power approach? Well, once you have a primary outcome, that's what you use to specify your null in either a 1 or 2-sided alternative hypothesis, for example, the mean or proportion. What's the effect size means? What's the deviation from the null hypothesis that's deemed clinically meaningful? Back to my blood pressure example, the effect size could be the difference between the 2 treatment groups of 20 millimeters of mercury for systolic blood pressure. What's the variability? For example, what's the standard deviation of the primary outcome of interest? And then what are the type 1 and type 2 errors you're willing to accept? Type 1 errors typically you'll see denoted as an alpha, and type 2 errors typically noted as beta. And I guess I do have one formula on this slide. Power is basically 1 minus your type 2 error. The only formula in the whole slide. And then the sample size is how much evidence you wanted to collect to verify your hypothesis. So I know a lot of this is review, but again, I'm just giving you an overview of things. So in this slide, this simple 2x2 table is looking at your errors. The columns are the actual the truth, and the rows are the decisions you're making based on your research study. So let's assume you're trying to assume that groups A and B, your null hypothesis that the mean systolic blood pressure in the placebo group is equal to the mean systolic blood pressure in the new drug. Your alternative hypothesis is that the new drug's mean value is different than the placebos. So if you don't reject the null hypothesis, and that's the correct answer because the null hypothesis is true, then you made a correct decision. And if your alpha was 0.05, then you're 95% confident that you made a correct decision. The other way you make a correct decision is if you reject the null hypothesis. So you state that your new drug is different than your placebo, and that's the truth. So that's a correct answer, and that's the power of the study. And then these other two diagrams, the errors. So if you don't reject the null hypothesis, but the alternative is true, that's type 2 error, 1 error. And in general, type 1 errors are considered more serious than type 2 errors. As the type 1 error increases, type 2 error increases, and vice versa. A lot of times you'll see your type 1 error set to 0.05, but it doesn't have to be. 0.05 is not a magic number. And your type 2 error will depend on the alternative hypothesis, test statistics, and sample size. So a good way to think about this, I like the analogy of a jury decision. So you can think of this as your null hypothesis is that there's no association between the defendant and the crime that was committed. So it's innocence. The alternative hypothesis is what the prosecuting attorney is trying to show, is that there is association between the defendant and the crime that was committed. So they're trying to show guilt. So the type 1 error would be if you convict an innocent person. Again, you claim there's no association when there actually was one. A type 2 error is when you quit a guilty person. So you claim there's no association when there is one. And the reason I like the jury analogy is this kind of shows why a lot of times you think a type 1 error is more egregious than type 2. In society in general, it's worse to convict an innocent person than it is to let a guilty person go free. So hope that was made sense. So other things you need for sample size estimation, we already talked about the topics, but I'm just going into a little more detail, is the effect size. So this is the size of the deviation from the null that we wish to detect in our sample. Back to the systolic blood pressure example, this would be wanting to show, for example, a 20 millimeter mercury difference between placebo and a new drug. It should be clinically or scientifically important. It's one of the most difficult aspects in trying to plan your sample size for your trial. And how do you get this done? How do you get this information? You can do a pilot study, a literature search, and if all else fails, take your best clinical guess or on the topic. Another term you may see is called a standard size or relative effect size. And what this is the effect size divided by the variability. For example, the standard deviation for a continuous outcome. And it's usually set between 0.1 and 0.5. And an example of interpreting this, say it's 0.5, it means the alternative hypothesis is 0.5 standard deviations away from the null. And because you're dividing, it's a unitless measure because you're taking the effect size divided by the variability. And that brings in the variability. So the greater the variability or spread in the outcome variable, the more likely it is the values in the groups will overlap, and then it'll be more difficult to demonstrate an overall difference between them. So in short, the more variable your data is, the more subjects you're going to need to show a difference between your groups. So the investigator may need to obtain an estimate of this variability for the power calculation. And again, how do you get that? Pilot studies, historical data literature, or your best clinical experience, or your best not to be clinical, but your best experience on the topic. And more complicated designs have multiple sources of variation. For example, repeated measures designs have within subject as well as between subject variability. So you could have multiple sources of variability. So this leads us into power. So what is the power? The intuitive definition is just the strength of your study. And power and effect size are directly related. With all other things being equal, the larger the effect size, the more power you're going to have. Similarly, the smaller the variability you have, the more power you have. The larger the sample size you have, the more power you have. And the more type 1 error you're willing to accept, the more power you have. However, it's pretty rare to see type 1 error go much higher than 0.05. Occasionally you'll see it to be like 10%, but you never see type 1 error, like 50% type 1 error. It would be rejected immediately. So on to the steps. So the reason I listed out as steps, even though there's not any formulas, this is the information you need to either enter into some software program or to bring to your statistician to have them calculate the sample size and power for you. So you need to state your null in either a one-sided or a two-sided alternative. So what that means is, what is the primary outcome for your study? Is it systolic blood pressure? Is it HbA1c levels? Is it the percent of people who quit smoking? Like, what is the primary goal of the study? Even though you'll probably be collecting a lot of information, you really want to focus on, you can have more than one we'll talk about, but ideally you have one primary hypothesis you power your study for. Everything else is secondary or exploratory analysis to be looked at. Based off your primary outcome, what's the test you're going to do? To do a sample size or power calculation, it's all based on a statistical test. The formulas differ. That's why I'm not showing you formulas. If you're planning to use a two-sample t-test, because you have the mean in group 1 and the mean in group 2, there's a formula for that. If you're comparing proportions and plan to use a chi-square test, there's a different sample size formula for that. If you have longitudinal data, meaning repeated measures analysis, there's a different formula for that. So you need to select the stat test that they'll use at the end of your study to answer your primary hypothesis. So what's the effect size and the variability that you want to find? Is a 20 millimeter mercury drop in systolic blood pressure considered clinically important? Or is it 30 millimeters of mercury? Or is it 10? That's the effect size you need to determine. How much type 1 and type 2 error are you willing to expect? And typically you'll see alpha or type 1 error to be 0.05. And if you're doing a NIH grant, the maximum beta or type 2 error you see is typically 20%, meaning that a power of 80% is as low as the powers typically go. The higher the power, like 90% or 95%, is much better. But NIH studies will typically accept power as low as 80%, meaning that type 2 error is 20%. And then we calculate our sample size. I see we have a question, which I will answer here in a second. I just want to go a couple more slides and then come back. Oops. So the outcome also depends on, is it a continuous outcome? We're looking at the means in each group, and then we need a variability. For a categorical outcome, you need estimates for the proportions in each group. If it's a survival outcome, you need the estimates of proportion of subjects surviving until some time in each group. And as I mentioned, there are a lot of software packages that will do sample size estimation. PASS, which stands for power and sample size, SAS, Stata R, SPSS. And for very simple ones like t-test and chi-square test, there are online calculators that will do that as well. So some additional things to consider, and I'm just bringing up topics that affect your sample size and power, is what is the goal of the study? Is it a superiority study, a non-inferiority study, or an equivalent study? I'm not going into details of what each of those are, but each of these different types do affect the number of subjects needed for the study. If people don't know, superiority is the most common. We're trying to show that, treatment A is better than treatment B. A non-inferiority trial is one where treatment A can be a little worse than treatment B, but it's not considered, as long as it's not too much worse, you consider it non-inferior. And equivalence is we're trying to demonstrate that the two treatments are equivalent. The easiest thing about equivalent studies is if you're trying to do a generic drug, you have to show that the generic drug is equivalent to the patent branded, GSK or Merck drug. The generic drug can't be worse or it can't be better. It has to be equivalent. So there are special formulas for that. The design of your study, is it a one sample study? Is it two samples? Are there more than two samples? Are the data independent? Are they independent groups or are they paired? Like a pre-post design. Is it longitudinal with repeated measures? There's crossover studies, dose finding. There's lots of different things that do affect sample size and power. You can have multiple endpoints. And I mentioned you really want to focus, I think, especially on investigator-initiated studies, on one primary outcome. I know a lot of investigators say, well, all these 10 outcomes I want to look at are important. That may be true, but you pay a penalty for it. The more outcomes you want to look at and power for, the larger your sample size is going to get. And it's probably going to get so large that the study will become not feasible. For example, if you had two primary outcomes you want to look at, instead of using an alpha of 0.05, you probably want to do 0.025 for each of the outcomes. So instead of a 5% chance, you want 2.5% chance per outcome to give you the overall 0.05. But what that means is smaller the type 1, 0.025 means you're going to need a lot more subjects to find a difference. You can do unequal sample size. You don't have to have equal sample size studies. I know I talked about the randomization process. I kept saying like, oh, half the people on treatment A and half the people on treatment B. It doesn't have to be that. You could have 75% of your people assigned to treatment A and 25% assigned to treatment B if you wanted to, like a 3-to-1 ratio. So that impacts the power. Dropout. Anytime you do a sample size and power calculation, the number of the programs come back and say, oh, you need 20 people per group. That number is the total number of people that you have data on. So if a study says, oh, you need a total of 50 people, but during the course of your study, 15 people drop out before they finish the study, that's not accounted for in a sample size calculation. You have to inflate that sample size to account for your dropout. We'll talk about that briefly a little more. We have non-compliance, non-response, interim analyses. If you plan to peek at your data once or twice before the final outcome, there's something called alpha spending function. So you have to look at your type 1 error and adjust that. If you plan to do, if you have three or more independent groups and you want to say we have 3 treatments A, B, and C, but the end goal of your study is to compare treatment A to B, treatment A to C, and treatment B to C. That's actually 3 tests. So you have to account for those multiple comparisons. Adjusting for covariates, number of available subjects, etc. So I just want to bring up dropouts, which I already mentioned. Dropouts are not directly incorporated into sample size estimation. So you estimate those during the design stage, and you need to increase the size of the enrolled sample size to account for dropouts. So for example, you could inflate your sample size by 20% if you think 20% of your subjects will drop out of the study before it completes. Number of available subjects. So let's take this example. A clinic sees approximately 20 patients per year with a given condition of interest, of whom 10% may refuse to participate in the study. So over 2 years of the study, the number of even possible available subjects for the study will be approximately 36. Let's say your sample size and power calculation came out to be 60 subjects. Well, you have to make some choices. I've seen investigators take that 60 and go ahead and do their study anyway, without thinking about, I don't even have the patience to fill this out. So although most studies need to balance feasibility with study power, the sample size should not be determined by the number of subjects available alone. Some things you would want to consider be, maybe you need to do a multi-center trial, or maybe you need to change your primary outcome, the one that's more feasible. If this primary outcome required 60 subjects, but you only have 36 available in a 2-year period to finish your grant. So when can power be smaller than you originally estimated? So this comes up when, say you do your diligence and do a sample size and power calculation prior to collecting your data. Statistician tells you, okay, we need 50 people total, 25 in each group. You do your study, you get 50 people the statistician told you to, and the p-value is not significant. Why is that? Well, the power and sample size calculation is only as good as the assumptions going into it. So if you make poor initial assumptions, then the power might not be valid. So for example, if you assumed that your standard deviation for your primary outcome was, back to systolic blood pressure, 10 millimeters of mercury, and then when you actually did the study, it was 25 millimeters of mercury, it was much larger than you expected, then your study isn't going to find an effect probably because it's underpowered. So sample size and power estimation isn't definitive. It's taking your best guess and best information on how the study will turn out. And hopefully it turns out that way, but sometimes it goes wrong. I shouldn't say goes wrong. It just doesn't go the way you thought it would. So again, wrong initial assumptions about the effect size or variability. The proportion of subjects who improve on placebo therapy may have been underestimated. I see a lot of researchers that want to say there's no placebo effect, meaning that, okay, the group of people are going to get on placebo. All their blood pressure is not going to change from the start of the study to the end of the study. So we're going to assume there's no change. Well, it could have changed by a small number, 5 millimeters of mercury. So there could be a placebo effect you didn't account for. Properties of the collected data do not match the original model. So for example, if you did a 2-sample t-test power calculation, that could assume the data is normally distributed. And if it's not, then your sample size of power calculation could be inaccurate. You may not have accounted for dropout for longitudinal studies or non-response. And the other thing I wanted to mention quickly is a high-powered study does not protect against all types of bias. So if your data has bad randomization, having a high-powered study doesn't fix these things, is what I'm trying to say. A properly powered good study, if it has bad randomization or poor blinding or bias sampling, etc., will not fix these problems. So reporting sample size estimation for your protocol. So if you're writing an IRB application, these are the things you want to include in your sample size estimation statement. You want a clear statement of what the primary objective of the study is. What significance level? I mean, what's your type 1 error you're willing to accept? What's the power? The type of summary or test statistic that we use for the analysis, whether it's a 1 or 2-sided test. And what's the clinical effect size you're trying to show? Make clear statements about the assumptions being made. How prior estimates of variance and the effects using the sample size estimation were obtained and their usefulness in the context. So did you get your information from a pilot study, or did you get your information from a literature? If so, reference that paper you used to get an estimate for your variability. Clear statements about the sample size calculation was adjusted. Did you account for dropout or loss to follow-up, etc.? And any other information that formed the basis for the sample size calculation. So I'm going to finish up here quickly, and then I'll get to the questions, the Q&A part. I just want to give you some examples. When you're writing your stat methods for a submitted manuscript or for an IRB application, here's some examples of them: poor write-ups and then some good write-ups. So the first one, sample size of 60 diabetic subjects has been chosen to provide adequate numbers of subjects for evaluating the treatments. These are actually examples that I've actually seen in IRB applications are very similar. What's poor about this first one? Well, it tells us there's 60 subjects, but there's no list of what's the power of this study. Is it 80%, 90%? What's the type 1 error? What's the primary outcome? It doesn't even list what the primary outcome is or the effect size. Going on to the second one, a sample size of 50 subjects, 25 per group, yielded 80% power to compare the placebo group to the active treatment. Well, this one tells us we need a total of 50 subjects, tells us what the power is, tells us what our two groups are, but what is it missing? Well, it's not telling us what our type 1 error is, and it's not telling us what the primary outcome is or what the effect size is. The next one, a previous study in this area recruited 75 subjects and basically found a p-value highly significant. Therefore, a similar sample size should be sufficient for our study. We just can't take somebody else's study that found a p-value and say, okay, they use 75, I'm going to use 75. You need to actually do a power calculation. What's the effect size you're trying to detect? This highly significant result may have been, maybe they found a difference back to my systolic blood pressure. Maybe it was an insignificant 1 millimeter of mercury difference between the two groups. I mean, you can find a highly significant result, but the clinical relevance might not be there. And the last one, a formal analysis was not done because there's no prior information to base the sample size estimate. That sounds really good and logical, but maybe before diving headfirst into a randomized trial, do a pilot study first, actually get some information, or at least take your best clinical guess of what you think it is. So I'm not going to read through these. I'm just going to highlight pieces. These are some examples of good write-ups. If you read through this, it tells us we need 16 subjects per treatment group. It says what the variability is. The standard deviation is 25 millimeters. It tells us it's 90% power. It's a two-sided test. 0.05 significant level tells us what the type 1 error is. It says what test they're using, a two-sample t-test. What's the effect size you're trying to show? They're trying to show a 30 millimeter difference in the visual analogs pain severity scale. So it tells us what our effect size is, it tells us what our two treatment groups are, a continuous and traditional OCP are two groups. And then it goes on to say they anticipate 15% dropout. So instead of recruiting 16 subjects, they're going to recruit 19. That way, when the estimated 50% people drop out, they'll have the required 16. The next example, again, they talk about we need a total of 140 subjects, 70 per group. It tells us what the power of the study is. It shows they want to detect the difference in the proportion of VTA. So this is the primary outcome, VTA. It tells us what the two groups are, placebo and active treatments, and what the proportions are in those two groups, 0.90 in the placebo group and 0.70 in the active group. They're telling us we're going to use a chi-square test that's two-sided and has an alpha level. So it's giving us all the information we would need to say, yep, I know exactly what the study plans to do. Another example, this is taken from JAMA published paper. It goes through, it says what our hypothesis is. A hazard ratio is the actual, this hazard ratio of 0.44 is the effect size between the groups. And it goes through and says what's the two-sided, alpha is 0.05. So it gives us all the information we would need. So in summary, carefully consider and state the hypothesis to be tested a priori. Select an appropriate statistical test like a two-sample t-test. Choose a clinically meaningful effect size. Provide an estimate of variability. Select the type 1 and type 2 error you're willing to accept. Calculate your sample size. Adjust that sample size, for example, from dropout, and consult and collaborate with a statistician. That's what we're here for, to help you work through your studies. And then here are some quick references. You need those. That's all for my talk. Now I'm going to open it up for questions and answers or anything. I don't know if Jay, if you have anything you wanted to say.
Very nice talk, Helen. There's just one question in the Q&A box. Do you want to answer that?
Okay. I don't know if everybody see the question I have? Is it showing?
I'm not
Or do I need
sure.
to read it?
Yeah, maybe we can read
Okay.
it.
I thought maybe it would show up. So this is tangentially related to sample size, but I was wondering, what is your opinion in regards to overall sample size and use of certain statistical tests on non-normally distributed data? For example, a t-test assumes a normal distribution, but I have seen some statistical texts and statisticians stipulate that with large enough sample size, the t-test is still valid due to central limit theorem. Well, others like to avoid dealing with this. What do I think? So you're right. I do think the central limit theorem kicks in with very large sample sizes. You don't have to do it. But if you think the data is not normally distributed, there are non-parametric sample size calculations out there. For example, the two-sample t-test mentioned, if you don't think your data is normally distributed, you could do a Kunselman-Whitney sample size calculation, which it's distribution free. It doesn't matter what the underlying distribution is. Another thing you can think about is, well, what if I think of my data as log normal? Well, then you could do a two-sample t-test, but use it on a log normal scale and still get adequate stuff. It does get tricky. As I mentioned, and I shouldn't say guilty of this, I do this as well. I will simplify sample size and power sometimes for very complicated repeated measures designs. It might be very hard to get, like I mentioned, you need, for repeated measures design sample size calculation, you should have within subject variability and between subject variability. A lot of times I have it hard when I work with investigators to have them give me any variability, let alone break it up into components. So I might have to boil it down to a simple paired t-test or something like that, because they don't have the information to provide me all these components of variability. So I know that's incorrect overall, but then I'll try to make adjustments. Like I might inflate that variability higher just to make sure I'm covered. And as I mentioned before, all sample size and power calculations are your attempt to do your best guess scenario. In the end of the study, nothing's ever going to match what it'll be a 1 in a million chance. The assumptions you put in your sample size calculation, like if you assumed I'm going to find a 20 millimeter mercury difference between my two groups and the standard deviation is 10, if that actually turned out to be exact at the end of your study, it's unlikely. But you're doing your best information to find, you're taking your best guess to get that. And a sample size just get you in the ballpark, meaning that the sample size, if it comes back and says, oh, you need 100 people, 50 per group, it's to get you in the ballpark where you need to be versus not having any information at all and you just saying, well, I don't know, maybe 20 people in each group would work when that's underpowered, or 1,000 in each group, which would be overpowered. So it's just the sample size estimation is trying to get you in a good ballpark of how many people I need to actually show my hypothesis, even though at the end of the study, it might not match exactly. I hope that was helpful. So trying to answer this question, yes, as larger sample size, the central limit theory kicks in, and a lot of things, parametric estimations like two-sample t-tests work fine. But if you really think your data is not normally distributed, there are power calculations for non-parametrics out there. Like I mentioned, a Wilcoxon-Mann-Whitney test, Friedman's test. I mean, I don't want to bore people with names of tests, but there are all alternatives out there. And if you're really into this, maybe I'm biased, but I think if you're really into doing sample size and power calculations, the past software I think is the best commercially available software because it does all kinds of things. If you really want to do stuff probably the best approach is, but it's time consuming. It's called simulation, which means you're basically have a statistician write a simulation program to do your power and sample size count. Time consuming to do a simulation power calculation, but it can be done for complicated studies. Like I mentioned, complicated repeated measures of mixed models. A lot of times, you almost, if you really want to get a good power calculation, you'd have to do a simulation study to do that. Any other questions anybody has? And I apologize for going over the time limit by 5 or 10 minutes.
No, you're fine, Alan. Any other question from our attendees? I do have like one very quick question, Alan. Like the example you gave, like the bad example, the last one, say there's no prior information that, so a formal analysis is not done. If the study itself is a pilot study, is that okay to have such statement?
Yes, I mean, if it's a pilot study, you should. Here's my view on that. And people, maybe you or Lan or somebody may disagree with it, or other statisticians. The goal of a pilot study, I think, is the main goal is work out the kinks in your process.
Yeah, to collect some initial data, right?
Just right. So collect initial data for power calculation. It's to collect initial data to do a formal power calculation. Yeah. You're not doing inferential statistics, in my view, for a pilot study.
Yeah.
So it should be all descriptive. So you don't need a power calculation at all because you shouldn't be doing inference.
Yeah.
If somebody's doing a pilot study and then trying to say get p-values and things like that, in my view, that's not correct because that's not formal power calculation. But also, I think more importantly, is just to work out kinks in the process. For example, this is not stats, but say your pilot study is, oh, I want people to come in every 2 weeks for 6 months. That's what I want to do my study. Well, the pilot study, you start doing that and you find out, well, gee, after 4 weeks, nobody's returning for visits. They think it's too much effort in that. Well, then you found out with pilot studies, like, asking people to come in for a physical visit every 2 weeks is too much. Maybe we should do it once a month. Mm-hmm. So the pilots to work out kinks and not only get estimates for stats, but it's the process of doing a study instead of investing a lot of time and money and effort into a full-blown, 100-person trial. And then halfway through it, you find out it's failing because you could have done a pilot and found out, oh, we have too many visits scheduled, or I wanted people to do all these things in one day. I think here's a good example. If you're looking at on a PAD patient, so people with like severe heart failure, and you want to do a study, you might have them do like tasks, like work on a treadmill or something like that. Well, it could be after they walk on the treadmill because they're so severely they're so worn out, they can't do the surveys you want to do. So the process might be do the surveys first and do the treadmill last. I mean, that's part of the pilots, like the order of doing your procedures that's what the pilots to work out, in my view. But also you get estimates of like mean and variability to do a power calculation.
Yeah.
But like I said, that statement, if you're doing a true pilot study, you shouldn't even have in my view, you don't even need a power calculation because you shouldn't be doing inference.
Yeah. Yeah. That makes a lot of sense. Thank you again, Alan.
Okay.
Very
great.
nice talk. And I'm sure the contents are very useful for our audience. So for our audience, you actually get a feedback survey. So please provide us some feedback, and that's very useful for us. And we will see some of you in 2 weeks for the next seminar. Thank you.
Thank you, Alan.
Bye, everybody.
Okay. Thank you, Alan. Bye.